In a previous video, we looked at the hyperbolic functions, sinh, cosh, and tanh, and I gave them as exponential definitions. Today, we're going to be looking at the inverse hyperbolic functions, and since the standard hyperbolic functions are exponential functions, then it stands to reason that the inverse hyperbolic functions are inverse exponentials, or logarithms. So what I'm going to do today is I'm going to derive them for you, and this is something you need to know how to do for the further maths course. For example, a 4-mark question might say, prove that the inverse hyperbolic sinh function is, and then it gives you the logarithm answer, which we'll get to. Okay, so we're going to have a look at these. So the first one we're going to look at is the sinh function. So for any inverse function, the process that we undertake is we swap the x's and the y's. So we've got y equals sinh of x, which is defined as being e to the x minus e to the minus x all over 2. So if we want to take the inverse function, then we're going to have to swap x and y. It doesn't actually matter at what point you swap x and y, but I'm going to start by doing it. So it's e to the y minus e to the minus y all over 2. So this is now the inverse of sinh. So if I were to plot that on the graph, that would be the inverse function. But I want to make y the subject of this. So that is what I'm going to do now. So first step, let's get rid of this fraction. And let's also get rid of this fraction. I know it's e to the power of a negative number, so it can be deemed as a fraction. So I'm going to times it all by 2e to the y. That'll get rid of the 2 here, and that'll also get rid of the negative power here. All right. The left-hand side is then going to become 2 x e to the y. This is then going to become e to the 2y, and that is minus 1. Okay. It's not massively obvious right now, but if you look closely, this is a quadratic equation in e to the y. So we've got e to the y there, we've got e to the y squared there, and then we've got a constant. So I'm just going to write that as the quadratic. So that's e to the y squared. That's what this term is. I'm going to bring that across the other side, so it's going to be negative 2x times e to the y, and then it's got minus 1, and that's going to equal 0. Okay, so this is now my quadratic equation. So to solve this quadratic equation, I'm going to use the quadratic formula. So that's e to the y equals, because it is a quadratic in e to the y, minus b, so that's positive 2x, plus or minus the square root of b squared, which is 4x squared, minus 4ac, that's going to be positive. And then that's all divided by 2a. I can pull a 4 out from this square root, that'll cancel with the 2 on the bottom. That 2 there will cancel with the 2 on the bottom. So I'm left with x plus or minus the square root of x squared plus 1. Okay, so there's my solution to this quadratic. Okay, but it is clear that the square root of x squared plus 1 is greater than x, because I'm taking a number, I'm squaring it, and then adding 1 to that number, and then I'm square rooting that. That is always going to be bigger, and that's a statement that you can state. This implies that x subtract the square root of x squared plus 1 will be negative, which in itself isn't a problem. However, the left-hand side is e to the y. E to the y can never be negative in the set of real numbers, so therefore we can reject x minus the square root of x squared plus 1, because you don't want a negative answer on the right-hand side. So therefore we can reject e to the y equals x subtract the square root of x squared plus 1. Okay, you can't just state that, you've got to justify it with this line here. Therefore, we're left with e to the y is equal to x plus the square root of x squared plus 1. And then finally, to make y the subject, we're going to take natural logs of both sides. And that will be y is the natural log of x plus the square root of x squared plus 1. That is the inverse sinh function. Okay, we would refer to that as r sinh of x. Okay, and it's defined as the natural log of x plus the square root of x squared plus 1. Okay. Notice there's no c here. It's not arc sinh like it would be for the trigonomic equivalent sine, because that is arc sine. For the hyperbolics, it's just r sinh. Okay, and it'll be r cosh and r tanh. All right. I don't think you'd lose a mark if you put a c there, but mathematically, it's not. There's no c in the inverse hyperbolics. Okay, so that is the sinh function, and that would typically be 4 marks or so. get that answer out. All right. Okay, the cosh one is slightly different. It takes a little bit more justification as to why we reject the negative root. So let's have a look at this. Same setup. Y is defined as cosh of x, but this time instead of minus e to the minus x, it's plus e to the minus x. In the shine example, I swapped x and y at the start, but this time I'm going to swap it at the end, just because it doesn't matter. So what I'm going to do is I'm going to take this equation and make x the subject. So the first thing I'm going to do, just like before, is I'm going to times the equation by 2e to the x, just to get rid of my fractions and negative indices. So the left-hand side is then going to become 2y times e to the x. The 2 cancels, I'm left with e to the 2x there, and then that's just plus 1. Okay, so a very similar equation to what we had before, except we've got a plus 1 here instead of a minus. This is a quadratic equation in e to the x, so we're going to get e to the x squared, which is that term. Subtract that across, so that's minus 2y times e to the x, and then we've got plus 1. That's going to all equal 0. Solutions to this quadratic, e to the x equals minus b, plus or minus the square root of b squared minus 4ac, all divided by 2a. And again, we can pull out the 4 from the square root and cancel with the denominator, so we're left with y plus or minus the square root of y squared minus 1. Okay. Now, in the previous example, in the square root, we squared a number, we added 1 and then square rooted it, and we could claim that that was bigger than this, so when we subtracted it, it was negative. Here that's not the case, because we've squared a number, subtracted 1 and then square rooted it. So this is actually going to be smaller than the original number, so we can't say y minus that is less than 0 anymore, because it's not. I'm going to have to play it a little bit differently. What I'm going to do is I'm just going to take logs of both sides, and I'm also going to swap the x's and y's at this point, because at the moment this is technically still the cosh function. It's just with something else as the subject. So now I take the inverse, and this can happen at any point. We swap the x's and the y's. That's the process for any inverse function. So we get y is equal to the natural log of x plus or minus the square root of x squared minus 1. Okay. The problem is at the moment this is not a function, because we've got 2 options in here. We've got a plus and a minus. And for a function, it has to have a single output for any given input. So what I'm going to do, there's a few different ways you can do this, but this is the way that I personally like to do it. I'm going to rewrite this logarithm as the natural log of x plus or minus the square root of x squared minus 1 under the number 1 to the power minus 1. Okay, so what I've done is I've reciprocated this, so it's 1 over, and then I've raised that to the power minus 1. So this is essentially the reciprocal of the reciprocal, which is the original. Okay, if you reciprocate a reciprocal, you haven't changed anything, and that's exactly what I've done here. But I've done this because now I can bring that minus 1 out as a multiplier, which is using a log law. And now what I'm going to do is I'm going to rationalise the denominator of this fraction. So at the moment it's x plus or minus the square root of x squared minus 1, so we've got a radical in there. So to get rid of that, I'm going to do x minus plus the square root of x squared minus 1. That is multiplying the inside of the log by the conjugate, if you like, of the denominator. Okay, so I'm left with that. So I've times top and bottom of this fraction by the same thing, so it's still equal to the contents of that, and the negative 1 power has come out as a multiplier using a log law. Okay, now multiply out the bottom there. It's going to be minus log. We're going to get x times x is x squared. This is a difference of squares, so the cost terms will cancel, which is why we've done what we've done, so that we don't have any radicals on the bottom. If that was positive, that would be negative, so it would be minus. And if that's negative, that'd be positive, in which case it's still minus. So in either case, you'll get minus x squared minus 1 on the bottom. And then top is x minus or plus the square root of x squared minus 1. Okay, almost there now. The denominator cancels, the x squareds there, so we're left with minus minus 1, which is just 1. So that is just negative the natural log of x minus or plus the square root of x squared minus 1. Okay, so what have I done there? What have I shown? Well, let's just look at where I started and to where I finished. Changing the signs, so if I change this plus to a minus, change that minus to a plus, then all I've done is I've times the log by -1. So I can conclude that the natural log of x plus or minus the square root of x squared minus 1 is exactly the same as plus or minus the natural log of x plus the square root of x squared minus 1. Okay. That's what I've shown in this line of working. These lines of working here justify this statement. And now I can say, well, I don't want two answers, I just want one. So I'm going to choose the positive log, so that I've only got one output for any given input. So this implies that y is equal to the positive natural log of x plus the square root of x squared minus 1. And there we go. Now that's the definition of r cosh. Don't forget, no c. So it's just ARCOSH of x. That's the logarithmic definition of the inverse cosh function. Okay. Graphically, we can also consider graphically what's going on here. If you recall from my graphs video on hyperbolic functions, the cosh curve looks like this, which is a many to one function. So when we inverse it, we had to kind of restrict the domain. Otherwise, you'll end up with a one-to-many mapping, which is not a function. So when we inverse it directly, we would end up with a graph that looks like this. Okay. And this graph is indeed this function here, the x plus or minus the square root of x squared minus 1. Through this algebra, we end up with this down here. And in choosing the positive log, what we are actually doing graphically is we are ignoring this bottom half of the branch, and we're just left with this, which is a one-to-one function, which is the definition of r cosh. Okay. So when you use the r cosh function, you've got to remember that the negative is also a solution. Okay, but we'll get to that when we look at solving equations with hyperbolics. Okay, so that was the most difficult of the three. The easiest one is next, which is the inverse tanh function. The process is exactly the same. We are going to create a quadratic equation which we're going to solve. So I'm going to times the whole thing by e to the x, just to get rid of the negative indice there, and then times by e to the x plus e to the minus x, just to get rid of this fraction here. That's of course the same thing as timesing by e to the 2x plus 1. Okay, it's doing the same process. All right. So the left-hand side is going to become e to the 2xy plus y, and then the right-hand side, this thing is going to disappear, and we're left with e to the x times the top. So that's e to the 2x minus 1. So it's a quadratic equation in e to the x, but there's no linear term, there's no e to the x, there's just the e to the 2x. So it makes it much easier to solve. Let's bring all the e to the 2x's across to one side. So e to the 2xy minus e to the 2x, that's going to equal minus 1 minus y. Let's times it all by minus 1 and factorise out the e to the 2x. So that's going to be 1 minus y equals 1 plus y. So times by minus 1 and factorise out the e to the 2x. So e to the 2x is that divided by that. And then we can log and then half to get x is equal to a half times the natural log of 1 plus y over 1 minus y. That is still the tanh function. I've not actually inversed it yet. So to do the actual inversing process, you need to swap the x and y. And we end up with y is equal to a half times the natural log of 1 plus x over 1 minus x. And that is the inverse tanh function, which is defined as r tanh, or r tanch, if you prefer that pronunciation. Okay. Good. Right, so let's just conclude with what we've done by looking at the graphs. So the first graph we looked at, first function we looked at was the shine function. So here we have y equals shine of x. It's a sketch of it. That was covered in a previous video. Its exponential definition is this. And then to inverse a graph, you reflect it in the line y equals x. So that looks like this. And this is the definition of r shine, which has that as a logarithmic definition, as shown earlier in the video. And because shine is one-to-one, r shine is also one-to-one. There's no restriction on the domain at all in that process. Okay, so that's a nice straightforward one. The cosh one, this is the graph of cosh of x, y equals cosh of x is exponential definition. The inverse function, we had to restrict the domain so that it was one-to-one. So the r cosh curve is not a perfect reflection of this because we first got to ignore that branch and then reflect, which is why we end up with this graph. Here's our logarithmic definition of r cosh, very similar to r shine, except we've got a -1 in the bracket as opposed to a +1. Okay, past that, it's the same definition. And then finally, the tanh function. This is the graph of y equals tanh of x. It's got two asymptotes horizontally at -1 and 1. Here's the exponential definition of that. It's just shine divided by cosh, which can be written as that. So you might see either of those exponential definitions for tanh. And then this is already one-to-one, just like shine was. So when you inverse it, you just reflect it in the line y equals x. It looks like this. The horizontal asymptotes become vertical asymptotes. It's an odd function, so it remains odd. And you can't plug in anything bigger than 1 or less than -1 into this, otherwise you'll be trying to log a negative number. So there's its logarithmic definition, as shown again earlier in the video. All right, thanks for watching. If you have any questions, please just pop them in the comments below, and check out other videos on my channel for maths contents for A-level maths and further maths. Thanks for watching.